Yesterday we started working on definitions of derivatives, the idea of derivatives, and by doing derivatives by definition. You have two different derivative definitions. Limit as t is approaching x of f of t minus f at x over t minus x. Or we can deal with limit as h approaches 0 of f of x plus h minus f at x all over h. And both of these will calculate your general derivative. When we are calculating the value of a derivative, f at a, f prime at a, which is also the slope of your tangent lines. Slope of the tangent line. We can go back to what we did before. Limit as x approaches a of f of x minus f at a over x minus a. So we have two methods that we have to calculate our derivatives. The value of the derivative, I would just go back to what we did with our slope function. Now, both derivative definitions, general derivatives have merit. And sometimes you can use one, sometimes you can use the other. It makes it a little bit easier. If we look at problem number 3. Problem number 3, I want to find the general derivative of f of x, or of e to the x. The general derivative for e to the x. Now, if we use f of t minus f of x over e t minus x, f of t is e to the t minus e to the x over t minus x, and we have problems with that because we don't know how to simplify that. So we go to the alternate definition. The limit as h approaches 0 of f of x plus h. So we have e to the x plus h minus e to the x over h. Now you might sit there and say, well, how is that going to help us? Well, how that helps us if we have to utilize a property of exponents. If I have x to the a times x to the b power, what does our exponent rule tell us we have to do here, Ozzy?
You can combine the terms of the x to the a b power.
A b power?
A plus b power.
A plus b power. Okay, so if we have x to the a times x to the b, that's x to the a plus b power. Well, this property also goes in reverse. If we take it in this direction, if we have x to the a plus b power, this is x to the a times x to the b, which now allows us to be able to rewrite e to the x plus h power. Liam, how can I rewrite e to the x plus h power? Utilizing that property. E to the 2x plus h. I am here, and I want to go back in this direction. How can I take this here and
e to the x plus e to the h, or times e to the h.
e e to the x times e to the h power minus e to the x power all over h. Now if we look at our numerator, we have a common factor that we could take out. That common factor is e to the x. So we can factor out that e to the x. So we have e to the x times e to the h minus 1 all over h. If I put in h for 0, or 0 in for h, we have e to the 0 minus 1. Well, e to the 0 is going to give me 0, or it's going to give me 1 minus 1, it gives me 0, and I have h on the bottom, which still gives me 0. So how does this help us? Well, how this helps us is all we're worried about here is h approaching 0. So my sub here is going to be 0 for h. This e to the x has nothing to do with h. So you can think of that as like a constant, and we can pull out front. Why do I want to pull out front? Well, it's just going to make this a little bit cleaner for me to look at. So we have limit as h approaches 0 of e to the h minus 1 over e to the h, or over h. Now, how do we solve that? Well, we don't really have a technique to solve that, but what we can do is go back to old school. And just clickety-clack it into our calculator. Let's type in the function in y1, e to the h minus 1, quantity e to the h minus 1 over h. So you have quantity e to the h minus 1 divided by h. And start doing values. What happens at point 1? And what happens at point 0, 1? What happens at point 0, 0, 1? What y value do we continue to get closer and closer to? What do we get closer to? 1. So this value here goes closer, gets closer and closer to 1. So we're left with e to the x times the value of 1, which is e to the x. So if we have a function e to the x, when you take the derivative, it's the exact same thing. If you have a function e to the x, when you take the derivative of e to the x, you get e to the x. It's sort of a unique function. Any other questions you have on any of the other problems? Front or back? Yeah? Number 1. is equal to x over x minus 1. So if we take a look, we have a limit as t is approaching x of f of t, which is t over t minus 1, minus f of x, x over x minus 1, and this is over t minus x. We have a complex fraction, we have fractions within the fractions. So we need to look to multiply top and bottom by a denominator that will, or a value that will clear out both of our denominators. So that is a t minus 1 and an x minus 1. So we're going to multiply both top and bottom, t minus 1, x minus 1. So if we distribute this, t minus 1's cancel on the first one. So we're left with t times x minus 1. Multiply through the second one, the x minus 1's cancel. So we're left with minus x times t minus 1. And our ultimate goal is to get rid of this t minus x, so I'm not going to multiply this out and then have to factor again. So we have t minus x, t minus 1, and x minus 1. Yeah, I thought you had a question. Using our distributive property, we have a limit as t is approaching x of tx minus t minus xt plus x. Still have our same factors. Well, if we take a look, we have a tx here minus an xt here. Using our commutative property does not matter. Our commutative property of multiplication, tx will equal to x times t. Okay, they're equal. So I can write this as t minus x, or tx here. So we have a tx here and a minus tx here. They go bye-bye. So we're left with a limit as t is approaching x of negative t plus x, t minus x, t minus 1, x minus 1. I want to get t minus x, not an x minus t, so I can factor out a negative 1 to flip them around. So now we have that common factor of t minus x, which will cancel. And then we can sub in x for t. So we have negative 1 over x minus 1 times x minus 1. Or negative 1 over x minus 1 squared. Any other questions? A lot of this turns into just algebraic skills at a certain point. Dealing with complex fractions. Anything else?
Number 2.
Hmm?
Number 2.
So we have a limit as t is approaching x of f of t 5 over square root of t minus f of x, 5 over square root of x over t minus x. Common denominator is square root of t square root of x. Square root of t cancels on the first one, square root of x cancels on the second one. So we're left with the limit as t is approaching x, 5 square root of x minus 5 square root of t over square root of t square root of x, t minus x. Once again, just distributing over both your terms. I'm going to factor out a negative 5 here just to turn these two variables around. So we have a limit as t is approaching x, negative 5 square root of t minus square root of x. Then we have square root of t square root of x. And we can factor down t minus x into square root of t plus x, square root of t minus x. Square root of x. So your square root of t minus square root of x cancel out. Subbing in t for everything, or x for everything, we have negative 5 over square root of x, square root of x, square root of x plus square root of x. Square root of x times square root of x gives me just x. Square root of x plus square root of x gives me 2 square root of x. So we have negative 5 over 2. X square root of x. Once again, it taxes your your algebraic skills to manipulate through. Alright, but as you can see, as you experienced as we went through this, very cumbersome to use your definition, derivatives by definition. So let's take a look at what happens to different limits here, or different derivatives. Now, you do not have to write down everything I threw up here. What you should write down is your basic results of what happens here. Because we'll take a look at what happens with the results. If we look at a function f of x equals x, and I take the limit, and I want to find the derivative. We have a limit as t is approaching x of f of t, which is t minus x over t minus x. So we have t minus x over t minus x, something by itself. These cancel, which gives us a value of just 1. If we take a look at x squared, we take the limit as t is approaching x of f of t, which is t squared minus x squared over t minus x. The top will factor. T minus x, t plus x over t minus x. T minus x's, they move to Texas. Okay, we put in the value of x for t, we're left with x plus x, which is 2x. So if I take the derivative of x squared, I get 2x. If we take a look at x cubed, we take the limit as t is approaching x of t cubed minus x cubed over t minus x. Now we have to remember how to factor difference of perfect cubes. So we have the limit as t is approaching x of, let's see, t minus x, t squared plus tx plus x squared over t minus x. Once again, the t minus x's, they move to Texas. So we're left with x squared, substituting x for t, x squared plus x times x, which is another x squared plus another x squared. So we get 3x squared. If we take a look at x to the fourth, we have the limit as t is approaching x of t to the fourth minus x to the fourth over t minus x. Factoring the top. Limit as t is approaching x. Let's see, difference of perfect squares. T squared minus, t squared minus x squared, t squared plus x squared over t minus x. The t squared minus x squared still factors, so we're left with the limit as t is approaching x of t minus x, t plus x, t squared plus x squared over the t minus x. Once again, the t minus x's, they move to Texas. So they cancel out. Putting in an x for t, we're left with x plus x times x squared plus x squared. So this gives me 2x times 2x squared, or 4x cubed. So my derivative of x to the fourth is 4x cubed. If we take a look at x to the sixth, all the fun's just beginning. We have the limit as t is approaching x of t to the sixth minus x to the sixth over t minus x, which is the limit as t is approaching x of, let's see, we can either do difference of perfect squares or cubes. I'm going to go the cubes. So we have x squared, t squared minus x squared. Then we have t to the fourth plus t squared x squared plus x to the fourth. And this is over t minus x. Did that because I could still factor this down into t plus x, t minus x. So we're left with the limit as t is approaching x of t plus x, t minus x, t to the fourth plus t squared x squared plus x to the fourth over the t minus x. T minus x's. They still move to Texas. Okay, so what we're left with, when we sub in, we have x plus x. Here we have an x to the fourth. Here we have an x squared times x squared plus another x to the fourth. So that gives me x to the fourth there. So we have x to the fourth. So this gives me 2x. This gives me times 3x to the fourth. So 2x times 3x to the fourth, I get a value of 6x to the fifth. When I had the derivative of x, I got 1. When I get the derivative of 2, or x squared, I got 2x. When I get the derivative of 3, or x cubed, I get 3x squared. The derivative of x to the fourth, 4x cubed. Derivative of x is 6, 6x to the 5th. Following the patterns of what we had, what would be the derivative of x to the 8th? Liam? Now, how did you come up with 8x to the 7th?
The power goes to the front, but the exponent is still on the back for it.
Okay? The exponent comes out front, and we subtract our exponent by 1. Well, let's see what happens when we throw a coefficient out front. When we throw a coefficient out front, well, let's take a look. We have the limit as t is approaching x of 5t squared minus 5x squared over t minus x. We can factor out the 5, which will give us t squared minus x squared over t minus x. If I want to, I can use my property of limits. That constant can come out front. So we have 5 times the limit as t is approaching x of t minus x, t plus x over t minus x. The t minus x's, once again, still move to Texas. I have 5 times, I have x plus x, which is 5 times 2x, or 10x is my derivative. So I still get the 2x. For my x squared, I still get the 2x. All I've done is I've multiplied by the coefficient 5. So if I take a look and follow that same method of madness, the derivative of x cubed would be what, Nate?
It would be 21x squared.
What's the derivative of x cubed?
It would be t cubed.
Yeah, I know, but what would just be if I had f of x equals x cubed? What would be the derivative? Put them all together that you're trying to give me. I'm trying to slow your brain down. What was the derivative of x cubed?
It would be t minus x.
Yes, but what's the result?
7 times 3x squared.
There we go. Making it way too tough. Slow your brain down. Okay, we have 7 times the 3x squared. So now we have the 7 times 3x squared, which would give us 21x squared. So we're still taking the derivative of our x cubed to give us 3x squared. We're still taking the derivative of our x squared to give us 2x. But now we're just multiplying by the coefficient of 5, whatever the coefficient is. So taking a look at this, we have our exponent rule for derivatives. If I'm in the form of ax to the nth power, a times x to the nth power, coefficient, variable, exponent. My derivative is I can multiply my coefficient times my exponent and then subtract 1 from our exponent. So if I have a coefficient here, we take our coefficient, multiply our exponent to our coefficient, and subtract 1 from our exponent. This is your exponent rule for derivatives. But you need to be in the form of ax to the nth power. If I take the derivative of a constant, let's think about a constant. If I have a constant, f of x is equal to 7. That's it. Well, I can rewrite this as 7 times x to the 0th power. Just tells us we have 0 factors of x. So if I apply this rule to this, we have 7 times 0 times x to the 0 minus 1 power. Yes, I get 0 minus 1, which is x to the negative first power. But I have 7 times 0, which is going to wipe out everything. Well, the key is to be able to get it into this form, ax to the nth power. Well, if I have 6 times the square root of x, what we need to be able to do is get it in the form of some constant times x to the nth power. Not divided by x to the nth power, times x to the nth power. So I need to be able to rewrite the square root of x. Well, if I have the square root of x, how can I rewrite that into an exponential value or form? Brandon?
1/2.
1/2. So my function turns into 6 times x to the 1/2 power. So now when I take my derivative, we have our exponent times our variable, and then we have to subtract 1 from the exponent. Six times 1/2 gives me 3. And then we have x to the negative 1/2 power. Now, the rules of thumb and how we're going to write our solutions here. Need to get it back into a radical form, and your solutions are not to have negative exponents. So you need to get it back into simplified radical form with no negative exponents. Well, if I take a look, I have a negative exponent there. What happens, what does the negative exponent tell us what we have to do? Where does it go when it's a negative exponent? We have a negative exponent. Where does it go? Anybody remember? Negative exponent. Yeah, it makes a fraction, goes down the bottom. If it's a negative exponent, if I have x to the negative 2th power, that's 1 over x to the 2nd power. So we have to remember our negative exponents. So this tells us this is going to drop us down to the bottom, so we have 3x to the 1/2 power, but I need to put it back into a radical form, 3 over square root of x. Now what I will tell you though, that you do not have to rationalize any denominators here, but you need to get it in a simplified radical form and no negative exponents. Well, if I have 7 over x to the 4th, how can I rewrite 7 over x to the 4th into an a times x to the nth power? Right now we're a divided by x to the nth power. So how can I rewrite 7 over x to the 4th? How does he have to rewrite 7 over x to the 4th? X to the negative 4th. So we have 7 times x to the negative 4th power. So to find our derivative, we take our exponent times our variable, and then subtract 1 from your exponent. Go ahead and find your derivative. Check your answer with somebody around you. Put your answers back into simplified radical form or no negative exponents. Nate, what did it come down to?
Negative 28 over x to the 5th.
That's correct. Because negative 4 minus 1 gives us x to the negative 5th. That's going to drop down to the bottom. Find the equation of the tangent line at x equals 4. Well, if I wanted to, I could go limit as x approaches a is f of x minus f of a over x minus a. Yay! If you want to. But, once again, what we talked about when we calculate the value of the derivative, that is also the slope of the tangent line. Which now allows us to sit here and look, let's take a look at this. What is our derivative of this polynomial? Well, what I'm going to do is use my exponent rule 3 times here, or 4 times here. So if I take the derivative of my polynomial, just continue to use your exponent rule. Take your exponent times your exponent times your coefficient. Subtract 1 from your exponent. Adam, what do you get for a derivative?
12x squared minus 10x minus 7.
That's correct. And if I have a constant, it's a 0. So to find my slope, it is the value of our derivative and what we're trying to find the value at. So the value of my derivative is the slope of the tangent line. So I can find my slope by taking 7 or 12 times 4 squared minus 10 times 4 minus 7. $149. What do we get?
145.
145. So the slope is 145. We also need to have a point of tangency. Which I'll call pi. P-O-T. Point of tangency. How do I find my point of tangency? Well, my x value is a value 4. How can I find my point of tangency? Dylan? My point of tangency for this function right here, I'm looking to find a point of tangency for this function here. I know the slope is 145. I know the x value is a value of 4. How can I find my point of tangency? Plug it in. Yeah. What is f at a value of 4? What's my function value at a value of 4? So we have 4 times 4 cubed minus 5 times 4 squared minus 7 times 4 plus 5. What do you get there, Evan?
I got negative 1,047.
Negative 1,047? Yes, no, maybe so?
Is that right?
I got 153.
153? Is 153 better?
Yeah.
So we have 4 and 153. We have, this is our slope, so we have m x minus x1 is equal to y minus y1. So we have 145. X minus 4 is equal to y minus 153. What this does is this eliminates a lot of limits, which makes life easier for you. Okay, I gave you a worksheet. It involves the derivatives. The first two I'm asking you to use definition of still, so you're going to have to do the limits for the first two. But for the other ones, you can use limit still if you want to, or you can use the exponent rule. Adios. Have a good day.